तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Good morning. Last few lectures we have been developing the theory for electrostatics, and we have reached up to Poisson's equation and energy in the field, and I did a problem last time. Today I plan to solve several problems which will work out the various parts of the equations we have derived. Last lecture I had started a problem and stopped in the middle. Let me repeat it. You were given a sphere of charge, and the charge density was rho of r. That is to say, the charge didn't depend on theta, it didn't depend on psi, it just depended on the radial distance. The sphere has a radius a, and you are told that electric field E of r is a constant. It is a constant inside sphere. So, in other words, if I plotted the electric field is up to this distance constant, and then it falls away. This is what I have been given. I do not know the value E naught, but in terms of this information I want to pin down what is rho of r. I am also told total charge is equal to some q. So, I want to solve this problem. Basically, I want to find E of r, and I want to find rho of r, and I want to find phi of r. So, in order to do this, you need to use the equations of electrostatics, and since the problem is spherically symmetric, the first idea that comes to us is, let us use Gauss's law. Well, if you use Gauss's law, what you get is that integral 0 to some r of 4 pi r squared rho of r dr. This 4 pi r squared is the surface area of a sphere of radius r. So, 4 pi r squared dr is the volume of a shell multiplied by the charge density rho of r. This is equal to q enclosed, which must be equal to epsilon naught times E naught. That is what Gauss's law tells us. At least it tells us this for 0 less than r less than a. If you took a Gaussian surface that was bigger than the sphere, then you would get a different equation. The epsilon naught, sorry, E of r times, sorry, here I have made a mistake. Let me just repeat. Charge enclosed is equal to epsilon naught times E of naught times the area. Okay, and the area is nothing but 4 pi r squared. Now, when you go outside the sphere, you have that E of r times 4 pi r squared is equal to charge enclosed divided by epsilon naught, but this charge enclosed is integral 0 to a 4 pi r squared or r prime squared rho of r. What I mean by that is, I have a radius r and I want to know what is the electric field coming out at this radius. The surface area of that at that radius is 4 pi r squared times the electric field. So, this is the flux. The flux is equal to charge enclosed divided by epsilon naught. The charge enclosed, there is no charge here. The charge is only inside the sphere of charge. So, only this portion corresponds to Q enclosed. So, that is this equation, integral 0 to a 4 pi r squared rho of r dr. Luckily, we are given this information. We are told that the total charge of the sphere is Q. Again, there is a 1 over epsilon naught. So, outside the sphere, we have E of r is equal to Q over 4 pi epsilon naught r squared. It is a very strange result, which again I am sure you are familiar with. The result is following. If I have a spherically symmetric charge distribution, the charge distribution could be anything. For example, I could have lots of charge out here, relatively little charge in the middle. But as long as it is spherically symmetric, if I measure the electric field further away than the sphere, the electric field I feel there is the same electric field I will feel if this entire charge was concentrated at the center. Because you look at this is Coulomb's law. So, regardless of the detailed shape of rho of r, the answer is Q over r square with the normalization constant. So, we already know quite a bit. Let me put down what we know. We have figured out what electric field is, because up to r equals a, the electric field is constant E naught. Beyond r equals a, electric field is falling off as Q over 4 pi epsilon naught r square. Now, of course, we do not know if the electric field is continuous there or not, but in the lack of knowledge I have just drawn it as continuous. So, I have almost already obtained the electric field. Now, let us go further on and see if we can obtain other quantities. Now, going back to this equation here, when I use Gauss's law inside the sphere, I got an equation that said the enclosed charge up to a radius r, let me put r primes here to indicate this is dummy variable. The enclosed charge between radius 0 and radius r, this charge alone gave me epsilon naught E naught times the surface area. This is not very useful, because I really want to know what rho of r is, whereas this is giving me what is called an integral equation in rho of r, and that is not an easy thing to solve. The way out of this is to convert from Gauss's law to the divergence theorem. The divergence theorem told us divergence of E is equal to rho over epsilon naught. Let us apply that and see if we get more information. In spherical coordinates, divergence is 1 over r squared del del r of r squared E of r, and this divergence is equal to rho of r divided by epsilon naught. Now, if this divergence looks rather strange, let me just remind you where it came from. Divergence in Cartesian says del del x of E x plus del del y of E y plus del del z of E z. That is what divergence is. But when you are talking about non-Cartesian geometries, something happens which is quite different from this. As you move in radius, what is happening is that the area between this angle will be some delta theta. The length of this arc itself is changing. That is because this distance is different from this distance, and the arcs are a function of the distance from the center of curvature. So, what happens is this area is small and this area is large. So, even as you go in the direction r, the area of your little box is changing. This does not happen in Cartesian. In Cartesian, if I will draw a cube or a cuboid. So, the area here and the area here are the same. So, the result is, if I was trying to work out divergence I got from taking the electric field coming in and the electric field going out and taking the difference in the amount of flux entering and the amount of flux leaving. Since the areas were the same, the difference in flux was equal to the same area times E of x plus delta x minus E of x, and that is why the area drops out. So, you get a derivative that acts only on the electric field itself according to the directions. But in a situation like this, what happens is this equation is wrong. Delta flux becomes the area at x plus delta x times electric field at x plus delta x minus area at x E at x. So, you see the area itself depends on x. And how does the area depend on x? Well, you know that for a sphere, if you fix the solid angles, if you fix delta theta and delta phi and you just ask what is the area goes as r squared, and that is what this r squared is. It is saying that it is not, you cannot pull the area out, the electric field is scaled by the area over which it is being measured. So, you have this r squared E, which is representing nothing else but area times E. So, that is where this equation comes from. You can read the appendix of the textbook where he derives it for you, not very well I must say, but still he derives it, and I do not think the derivation is very important. So, we have this equation and we would like to solve it. Now, solving this equation is easy. Just take the r square to that side. This E of r is known to be E naught. Differentiate this, what you get is E naught times del r squared by del r, which is twice E naught r. So, what you get is twice E naught divided by r is equal to rho of r divided by epsilon naught. E naught is known, r is known, epsilon naught is known, so you can calculate rho of r. So, it says that the electric field may be constant, but charge density is not constant. In fact, if I plotted charge density on this curve, I will draw it as a dashed line. The charge density is going to look like a 1 over r curve. And then it drops abruptly to 0 beyond A. This is what rho of r is. We have calculated rho. So, now let us try and use rho to calculate q. As you can see, we assumed q to define the electric field outside r equals A, but this q must satisfy the following equation. Q must be the volume integral of rho. In other words, it must be rho of r times 4 pi r squared dr. This is dV and this is rho. But we know what rho of r is now. We have already calculated it. So, we can substitute. So, it becomes integral 0 to A times twice E naught epsilon naught over r times 4 pi r squared dr. 1 r will cancel and we are left with 8 pi E naught epsilon naught. I have taken all the constants out, integral 0 to A of r dr, which is A squared over 2. So, the final answer becomes epsilon naught E naught times 4 pi A squared, and that is not surprising at all, because we already had from Gauss's law that surface integral E naught or surface integral E ds was equal to q over epsilon naught, which would have said that E naught times 4 pi A squared was equal to q over epsilon naught. So, they are saying the same thing, but in a certain sense it is saying something useful. You see, I had drawn two curves here. I had drawn E naught as constant and I had drawn this curve and I had joined them, but I had no real proof that they were to be joined. It could easily have been that the curve was here and jumped up and became this, but that is not possible, because by calculating charge from the rho that we calculated given E naught, the electric field just outside the sphere turns out to be exactly in agreement with what you calculate just inside the sphere. So, it means that in fact the curve is continuous. Now, from this we can calculate potential, that is easy. all you have to do is integrate phi of r is equal to minus integral E dl up to r, and the reference point is infinity. So, it becomes integral r to infinity E r dr. The region outside the sphere we already know because it is nothing but Coulomb's law. So, phi of r is equal to q over 4 pi epsilon naught r for r greater than a. For r less than a, the potential phi of r minus phi of a must be equal to the amount of work done against a constant electric field. In other words, is equal to E naught times r minus a minus r. Since E naught itself is nothing but q over 4 pi epsilon naught a, this is q over 4 pi epsilon naught a times a minus r. So, phi of r finally becomes q over 4 pi epsilon naught r if r is greater than a, and it becomes q over 4 pi epsilon naught a plus q over 4 pi epsilon naught a times a minus r for r less than a. So, this is the solution we need if we want to solve the problem of a charge distribution that has constant electric field. The important thing to realize is it is not natural for a sphere to have constant electric field. To achieve this constant electric field, you actually have to have a very singular charge distribution. Only if the charge distribution is very spiky will your electric field be uniform. Okay, let us do another problem. This problem is very straightforward, but worth understanding. Supposing I put a charge q in the middle of a hollow sphere, and the hollow sphere has an inner radius a, it has an outer radius b. So, this region is air, this region is metal, and this region is air. So, the metal is in between two regions of air. Furthermore, the metal region is neutral, that is no net charge. Okay. Now, what I want to know is what charge distribution can exist inside this metal that will minimize the stored energy, minimize the energy in the field due to this charge q. Now, let us back up a bit. If I have only a charge q, then I know that the potential is q over 4 pi epsilon naught r. The electric field is the radial electric field, which is q over 4 pi epsilon naught r squared. So, the energy in the field would have been integral mod E r squared times epsilon naught over 2 dV. That is, energy density in the field is epsilon E squared over 2, and I would have taken that integral from 0 to infinity. There is something sneaky about what I am doing, because if you remember how we calculated this epsilon squared over 2, we said that the energy to bring the first charge in was 0, yet I have got a single charge in there and I have calculated energy in the electric field. So, this energy that I am talking about is the energy that exists around a charge. That energy was already there, I did not have to do work to create it. When I put charge together to make a point charge of charge q, this is the energy in that field. So, now if I have this energy in a point charge and I now put a spherical conducting shell around it, how is that energy going to change? I am going to do this problem in two different ways, and it is worth understanding the two different ways. First way, I will use Gauss's law. Well, I will say I have a charge q and I have an inner radius a and an outer radius b, and I will put an imaginary Gaussian surface, a sphere of radius r. Now, this is inside the metallic region, and we have already discussed that inside any metallic region I cannot have electric field. So, surface integral E dot ds is 0, because the surface is entirely inside the metal, metal cannot support any electric field. So, that means q enclosed is equal to 0. Furthermore, there is another calculation you can do, which is I can draw two of these Gaussian surfaces and I can talk about the region between them. In that case, it says surface integral S1 minus surface integral S2 is equal to 0. Because each of them is separately 0, the difference of them is also 0. So, the charge enclosed inside any such sphere is also 0. This is a problem. There is no charge in the metal, but there is no charge enclosed. The charge must be somewhere, and the only place the charge can be is on the inner wall of the metal. So, there is a charge minus q on the inner wall. And if we draw a Gaussian surface outside the sphere, then total charge enclosed, well, the charge on the metal is 0, because metal has no net charge. Charge at the center is q. So, out here q enclosed is equal to q. So, from Gauss's law, what we find is the electric field E r as a function of r is equal to q over 4 pi epsilon naught r for r less than a. It is equal to 0 for a less than r less than b, and it is equal to q over 4 pi epsilon naught r for B less than R. It is just coming out of the application of Gauss's law. If I apply Gauss's law inside the air, I find the first result. If I apply Gauss's law inside the metal, I get the second result. If I apply Gauss's law in the air outside the sphere, I get the third result. So Gauss's law solves the problem for us. But I want to look at this problem slightly differently. Now we had derived last lecture that the energy in any cloud of charge, cloud described by rho of r, is given by volume integral rho of r phi of r dV with a factor of 1/2 in front. We derived this by bringing charge slowly from infinity and building up this cloud, and as a function of time, as we brought the charge, the potential at every point built up linearly. And the amount of work we did was equal to the potential at any given time t. So what happened was that in a certain sense we were measuring the area under the triangle, and that is where the factor of 2 came, because this rho times phi in a certain sense measures the area of the rectangle. Of course this axis is time and not rho, but the way I defined my derivation, charge was brought in time. So in a certain sense this also represents rho. So this was the derivation we did, and we obtained that the total energy was 1/2 rho times phi dV. But in our current problem we do not know rho. So we would like to get a better expression for this. Let us see if we can do that. Now we have one expression from Gauss's law which tells us that divergence E is equal to rho over epsilon naught. So I can substitute for this rho by epsilon naught times divergence of E. Let me do that. So this becomes equal to 1/2 volume integral epsilon naught divergence of E times phi dV. Now this divergence can be combined with phi. The reason is phi times divergence of E can be written out. It is equal to phi times del Ex del x plus phi times del Ey del y plus phi times del Ez del z. Now I know from my calculus that when I have a product of terms and I take the derivative of the product, this is one of the terms that comes out. So I can write each of these as del del x of phi Ex minus Ex del phi del x plus del del y phi Ey minus Ey del phi del y plus the third term del del z phi Ez minus Ez del phi del z. That is because if I take the derivative of this, it gives me this term plus this term. Now this term and the corresponding z term will give me I will take the epsilon naught out. So, these three terms will give me divergence of phi times E, because you can see that is what it is. Phi times E, the x component is phi E x, the y component is phi E y, and the z component is phi E z, and this term will become minus E dot grad phi. Well, we are almost done, because I can now use the divergence theorem on this piece, and here is what I get. Your book has the same derivation, so you can check with it. What you get is epsilon naught over 2 surface integral phi E dot ds, applying the divergence theorem here, plus epsilon naught over 2 volume integral E dot E dv. That is because minus grad phi is nothing but E. If we go far away enough, phi times E is going to go to 0. So, this term you can drop. And so, this integral, which involves knowing both charge and potential, can be reduced to a simpler form. It is equal to volume integral epsilon naught E squared over 2 dv. And the interesting thing is, you can give an interpretation to this. Here the energy in the field was due to the fact that we brought charge in against a potential, but here the charge is no longer visible, the potential is no longer visible, there is only a field here, and we are saying that at every point in space, due to the presence of field, you have a certain amount of energy present, epsilon naught E squared over 2. This particular form is very convenient, and we are going to use it just now to solve our other problem, but it will keep getting used, so keep it in mind. I want to say, supposing I knew that there is some charge distribution rho in the metal, then I can apply Gauss's law again, and what would I get? I would get that E of r is equal to q over 4 pi epsilon naught for a less than r, sorry, b less than r, and for r greater than less than a. That is, for regions inside and regions outside, it is nothing but Coulomb's law. In the region of the metal, I am going to assume some charge density, I do not know what it is. So, it is going to be q plus integral a to r rho of r prime dv, okay, divided by 4 pi epsilon naught r square. That is what Gauss's law will give us, because it is going to be charge enclosed, and what is the charge enclosed? It is q plus, really I should write this as 4 pi r square dr, I was writing it as dv to make it clear, integral a to r rho of r prime 4 pi r prime square dr prime. This is for a less than r less than b. This is completely general. If I knew rho, this is true. But now let me write down the energy associated with this field. I will call it U is going to be equal to integral 0 to a ER squared epsilon naught over 2 dV plus integral a to b epsilon naught over 2 dV plus integral b to infinity ER squared epsilon naught over 2 dV. So, there are three parts: the part that corresponds to the inner air region, the part that corresponds to the middle region, and the part that corresponds outside. And regardless of whatever charge I put down for the metal, this region and this region are fixed. That is, the energy in the field is not a function of what I chose for the charge distribution inside the metal. Any charge distribution gives me the same Coulomb's law in region 1 and region 3. The only thing that the charge distribution can change is region 2. So, I can write U is equal to U1 plus U3, these two regions, plus U2, and this is fixed, and this is function of rho. The second thing that is very obvious from this integral is that I am talking about something that is always positive or at worst 0. E squared cannot be negative. So, when I take the integral of something that is either positive or 0, the integral is always positive or worst case 0. So, I have that the total stored energy is equal to some fixed part plus one more part that is either 0 or greater than 0. If you have studied anything about gravitational systems and friction and all those kinds of mechanics problems, you know that systems like to reach a state of lowest energy. If you want to ask what is the lowest state of energy for this system, the lowest state of energy would be if U2 were 0. That would be the lowest energy state. It cannot be negative, so best it could be 0. But what does it mean if it is 0? It means that ER equals 0 for all A less than R less than B. ER is 0 everywhere inside the metal, which is nothing but what Gauss's law told us. Gauss's law gave us this result, but the result of Gauss's law is really saying nothing more or less than that if you allow an electrostatic field problem to stabilize, if you allow the charges to reach wherever they want to go subject to constraints, then the charges will arrange themselves in a minimum energy state. It is a very important idea, and you will find that a lot of problems can be understood if you realize that ultimately electrostatics is about minimum energy states. Okay, let me do a third problem now. And this third problem is fairly interesting. I have a ring of radius A. The ring has a charge lambda coulombs per meter. This ring, this charge ring, has a center of symmetry, this is the z axis, and at t equals 0 I put a charge q and I give this charge a velocity in the z direction. velocity v naught. The question is what happens? Okay. What happens to the charge in time due to the electric field? Let us work it out. Since the charge is on the z axis, it will remain on the z axis because the forces are all symmetric. So, there is no force trying to send it away from the z axis. So, we need to know the force on the charge at any value z. I can work out the potential. Phi of z is going to be equal to, I am at a distance square root of r squared, sorry, a squared plus z squared, that is the length, that is this, it is given by Pythagoras' theorem, z squared plus a squared. I have 1 over 4 pi epsilon 0, and the charge, the total charge is 2 pi a times lambda. Now, this is one case where you can see how easy it is to work with electrostatic potentials. We took a lot longer to calculate the electric field, whereas the electrostatic potential I could write down by just inspection. Once I have got phi, I can calculate E. The electric field is along the z direction, E z of z is equal to minus del phi del z is equal to 1 over 4 pi epsilon naught, and I will put this here 2 pi a lambda, and then I have to take the derivative. There is a minus sign coming from here and there is a minus sign coming from the derivative. So, those two signs cancel out. So, I get half over a squared plus z squared to the power of 3 halves times derivative of a squared plus z squared with respect to z, which is 2z. The 2 cancels the half, and so I get 2 pi a lambda divided by 4 pi epsilon naught z divided by a squared plus z squared to the power of 3 halves. So, the electric field, assuming that this lambda is positive, is pushing away from the ring, and it is pushing away from the ring in both directions, and the electric field along z is 0 at the origin. If you plotted E z of z, and I will plot it on this plot itself, in this figure itself, it will be something like this. So, it reaches a maximum. The maximum value it reaches is approximately where z is of order a. That is where z over a squared plus z squared becomes a maximum, and then it falls off, and you can see it falls off as 1 over z squared, because for large z you can neglect the a squared. So, it is z over z cubed, z squared to the power of 3 halves is z cubed. So, z over z cubed is 1 over z squared. So, it is Coulomb's law very far away, but the electric field actually grows as you go close to the, from close to the ring. Now, let us assume lambda is greater than 0. Okay. It is perfectly general. There are two cases. One is q greater than 0. If q is greater than 0, the charge starts moving, and as it reaches any point, it keeps seeing an accelerating electric field. The force on the charge is equal to q E z is also greater than 0. This is the force along z. So, you have m dv dt along z is equal to fz is greater than 0. You started with a Vz that was greater than 0 and it keeps increasing. So, this is a kind of such system where you're in z, or in time I should say. It started with a velocity v naught and it increased and saturated. This particle with a charge q escapes. Well, by that I mean the charge starts leaving, speeds up and goes away to infinity. It does not return. Now, what happens if q is less than 0? Now, you can see fz, which is equal to qez, is less than 0. Therefore, you start with some velocity, you start slowing down. You reach some maximum amplitude, maximum height z, and then you start coming back. Then you go to a maximum negative height and you come back, and so you expect oscillations. Can we see that? Well, let us write out the force equation. Force equation says m dvz dt is equal to qez, which is given by, we already have the form for q, so m dv dz, this is the force, rate of change of momentum, is equal to some constants which are negative. Lambda is assumed positive, q is negative, so this whole thing is negative, times a function of z. This is a function of z. You must be very familiar with this kind of equation when you have done the simple pendulum. There is a standard way of solving such problems. You just multiply both sides by Vz. So, you get mVz dVz dt is equal to qEz, which is a function of z, times Vz. But Vz is nothing but dz dt. mVz dVz dt can be written as d dt of 1/2 mVz squared, that is rate of change of kinetic energy. The other side can be written as, well, I will not write it out yet, it is equal to the same expression qE dz dt. Now, let me integrate both sides with respect to time, that is, I will just multiply through by dt. So, what do I get? I get that d dt of 1/2 mVz squared is equal to minus q d phi dz dz dt, which can be written as minus d dt of q phi. So, this is your kinetic energy, This is your potential energy. So, you can combine the two together, you get d dt of 1/2 mvz squared plus q phi equals 0. Or something which is very obvious, I can define a quantity E called m vz squared over 2 plus q phi of z equals constant. This would be my total energy. This is kinetic energy. This is potential energy. So, clearly what is happening is that the total energy of the particle is remaining constant. As the particle moves in z, it can exchange kinetic energy for potential energy or potential energy for kinetic energy, but the sum of the two must be a constant. This is extremely similar to Keplerian orbits, very similar to gravitational orbits. It is exactly the same problem. It is also a problem of a pendulum. Now, given all this, what can we say about the orbits? Initial kinetic energy was v naught was the velocity. So, initial kinetic energy was m v naught squared over 2. Initial potential energy was q phi at z equals 0, which we can work out here. We already have the form for q of z. The final velocity is 1/2 m v z squared, and the final potential is q phi of z. What this really means is, supposing I want to look at orbits that manage to reach infinity. At infinity, this becomes 0. The potential energy due to the electric field keeps reducing as you go further and further away. So, it is equal to 0 when you reach infinity. This piece becomes what is called escape velocity. The same idea as escape velocity for a satellite leaving the earth. There you would be talking about gravitational potential energy, and you would be talking about kinetic energy of the satellite. So, this is the velocity. I won't escape velocity is probably the wrong term. I would say it is the terminal velocity or asymptotic velocity. This is my starting velocity and this is my starting potential. So, what it means ultimately is I am inside a potential well, because my particle is being attracted back by the charge, by the charged ring. So, I can draw a potential energy curve in Z. The potential energy curve in Z says that very far away the particle has 0 potential energy, no charges have any effect. Very close, I have particles of opposite charge, they actually have negative potential energy. So, this is my potential energy. I now take a particle with some kinetic energy. Let us say I took so much kinetic energy. This would be my 1/2 m v naught squared. If I took it, then this is my total energy. My system conserves total energy. E equals 1/2 mvz squared plus q phi of z is constant. So, as the particle moves in z, this is not perfectly parallel, but it should be, the total energy of the particle does not change. So, the particle initially has a strong velocity, but as it moves further and further in z, its velocity keeps reducing, or rather its kinetic energy keeps reducing. And finally, the kinetic energy reaches 0. When it reaches 0, the particle has reached its highest point. At that point, it has no velocity left, it just has potential energy. So, it turns around and falls back. So, the particle goes up, turns around, comes back down, goes up, turns around, and does an oscillation. If on the other hand I had more energy, the points where it turns are further apart. If it has less energy, the points where the particle turns back are closer apart. But supposing the particle had too much kinetic energy. If it had kinetic energy greater than this amount, then even no matter how far away it goes, there is always some amount of velocity left, some amount of kinetic energy left, and this is a particle that has greater than escape velocity with respect to the hoop. So, you will get trajectories where particles leave, come back and oscillate, and you will have other trajectories where the particle just goes away. All of this is very analogous to mechanics. It is very similar to what you see in a pendulum, it is very similar to what you see in satellites, and it is very similar because the equations are very similar, and it is always important to know the different parts of physics have the same equations, because it makes it easier to study.